Example 16.4. In this example, a 2-meter long with a 0.3 centimeter diameter electrical wire extends across in a room which is maintained at 15 Celsius. Heat is generated inside of the wire as a result of a resistance heating, and the surface temperature of the wire is measured to be 152 Celsius in steady operation. Also, the voltage drop and the electrical current through the wire is measured to be 60 volts and 1.5 amps respectively. In this problem, we disregard any heat transfer by radiation. Our goal is to determine the convection heat transfer coefficient for the heat transfer between the outer surface of the wire and the air in the room. So to start with the problem, let's do a schematic. So this is going to be the wire that we have, and as it was explained, there was a resistance that it goes in here, and that resistor has a certain voltage drop and current, and that creates a certain amount of electrical power. That electrical power gets conducted into the wire, and which makes a constant temperature over here to be 172 Celsius. 152 Celsius. All right. So this electrical power is maintained in such a way that the surface of the wire exposed to the air remains constant. Then we have air that goes across from over the wire, and that air produces a certain amount of heat transfer coefficient, and we have a room that is maintained at a certain temperature. In order to evaluate this problem, we simply say that the amount of heat transfer that is created by the electrical resistance has to be equal to the amount of heat transfer by convection in order to maintain balance of energy. So we simply say that the amount of electrical power that we're going to have, which is given by the resistance, has to be equal to the amount of heat rate by convection. Okay, so let's start by calculating what is the value of the electrical power. So the electrical power, it is simply going to be the voltage times the current that we have across the resistance. So in that case, we got 60 volts and we have 1.5 amps. That gives us 90 watts. The amount of heat transfer rate due to convection is also going to be equal to 90 watts, since by balance of energy we make these two equal to each other. We also know that the definition of the heat transfer by convection is equal to the amount of the surface area, the heat transfer coefficient due to convection, and the difference between the surface temperature and the ambient temperature. So for this particular case, we have that the surface area that we evaluate is going to be the one surrounding the cylinder, basically the one that is in touch with the fluid. Notice that we're neglecting what happens at the end of the wire. So our surface area in this case is simply going to be pi dl, where basically this is your diameter and this is the length of your wire. Okay, in that case, using the values, we find that the surface area is equal to 0.01885 meters square. Our goal is to find the convection heat transfer coefficient. So we solve this equation for that. So H is simply going to be the heat transfer rate due to convection divided by the surface area and the change between the temperature of the surface and the ambient temperature. So we have this to be 90 watts. The surface area is 0.01885 meters square. The surface temperature is 152 Celsius and the ambient temperature is equal to 15 Celsius. So we plug this in and the value for H is given as 34.9 and the units are going to be watts m squared Celsius, or it could also be written as watts m squared. Okay, remember these two are equivalent to each other, but because when we multiply by a delta, and a delta of Celsius is equal to a delta in Kelvin. Also note that this problem didn't use any radiation, so when we evaluate the value of H, is only for convection.